Last session, we ended off on the hydrozone reaction. And are you ready? Okay. So we ended off on the hydrozone reaction, and essentially we reacted H2N NH2, which is called the hydrazine, and we kind of like replaced it with the O of a ketone. And that final product is called the hydrozone. And the way I said is easy to remember it is hydrazine, it goes in, and then hydrozone, it goes out, or you can do it the way I like to remember it. And so hydrozone, snap, that's the final product. It's dumb, I know, but that's how I remember it. So, all right. Questions, comments, concerns, anything? Okay. So the next reaction we're going to talk about, it's technically not another reaction, but sometimes we'll see this, but we will have excess. So what do we do if we have excess? We have a ketone. We have H2N NH2. And we're going to have either acid or base. It doesn't really matter. So this time, let's just say NaOH. Right? If he says excess under the ketone, we're actually going to make the product that we think we would get if there was no excess, which looks like this. So this is the hydrozone. But then we're going to react one more time, and we're going to get this really weird looking thing where what we've essentially done is we've taken the other nitrogen and we've added the ketone body to it as well. You won't need to know how to name this or anything. You just have to know that if there is excess, it's not exactly the same as the regular hydrazine reaction. There's going to be that extra step at the end. It's still technically the hydrozone reaction, but this isn't called a hydrozone, but you won't have to worry about what it's actually called. It has a really big, ugly name. I don't remember off the top of my head. One time I like jokingly told a student, like, you have to know the name, and he looked it up and he like was in a cold sweat, and I was like, I'm kidding. I promise you don't need to know that. Question. All right. Are we okay with this? If we see excess, we know what we're going to do? All right, cool. So the next reaction on our list is the Phenyl Hydrazine. And we briefly talked about this last time. So again, I'm just going to show you like the shortcut reaction. So we can start with either a ketone or an aldehyde. And this time I'm going to draw a super long arrow because we're reacting with H2N, NH, and then a benzene ring. Does anyone remember what the name of this is? Phenyl hydrazine. Yay. Okay, so again, we can use any catalyst we want here. Let's say NaOH because we haven't done bases in a while. So all we're going to do is replace the O with one of those nitrogens. So now, last time when we did the regular hydrozone reaction, both ends were exactly the same. But here, we have nitrogen 1, nitrogen 2. So which of those nitrogens do you think will be the nucleophile? The yellow one or the red one? Why? What do you think? Okay, is that a good thing though? There's a lot of bulk going on there. So this position is actually really terrible because there's just way too much steric hindrance. This is not going to be a good nucleophile. So instead, we're going to use these lone pairs. So this nitrogen is going to be the nucleophile. And again, it is very, very important that you know what specifically is a nucleophile, what specifically is the electrophile, so that you know what attaches where. So in the final product, we're going to keep the bottom half of our ketone exactly the same. We're going to make a double bond. Oh, that's like instinct already. So we make a double bond and we're going to attach the nitrogen on the end. We get rid of those hydrogens. We have NH and a phenyl. So it's just like the regular hydrozone, but with an extra group attached. So what do you think this product is called? Phenyl Hydrazone. Perfect. So again, this is super similar to what we did last time. Nothing like huge and new and exciting. But are there any questions at all? Nor my iced tea, yes. Whenever I remember that they're there, I'm just gonna throw at you. Funny story. I got evaluated last session, and my boss during our meeting was like, didn't say anything, and then at the very end was like, "Do you often throw candy at people?" I was like, "No, it was like a one-time thing." He was like, "Okay, because you can't do that." I was like, "Okay." Anyways, it wouldn't be a session without a side story. All right, so let's move on to the next reaction, which I believe on your list is the enamine, right? The oxime? Okay, we'll do that one first. So the oxime, that sounds ugly. Again, we're going to start with a ketone. This could have also been an aldehyde. And we draw our lovely arrow. And our nucleophile is going to be HO and H2. Does anyone want to guess what this nucleophile could be called? Hint, it's the one thing in this chapter that the naming makes sense. No. Good, like, detect the reasoning skills, but think about the two functional groups that are here. Close. Okay, so some people said amino alcohol, but we're going to switch around the order. So it's going to be a hydroxyl amine. Oh. So it's a hydroxyl plus an amine. So now the second spicy part of this reaction is now we have two heteroatoms. We have an O and an N. Which of those is going to be the nucleophile? NH2. Why do you think so? It is. Do you know why? If not, it's okay. Yes. Perfect. Okay, so I'm going to write a little note up top here. So nitrogen is the better nucleophile because it is less electronegative. And now that might seem kind of counterintuitive because we're like, oh, nucleophiles tend to be electronegative atoms, right? But electronegativity is essentially assessing how strongly you hold on to electrons, right? So if oxygen is holding on to its electrons even tighter, it doesn't want to make a bond. So it's not as good of a nucleophile. What trend is that similar to from a couple chapters ago? Think chapter 12-ish. Yes, exactly. So it's a very similar trend for acids and bases. So bases are stronger when they're less electronegative, and then acids are stronger when they're more electronegative. So just know that those are similar trends. And then we can use any acid or base as a catalyst. So again, let's just say NaOH. I'm in a basic room today. But Thank you. Thank you. Okay, so again, just like all the other reactions, excuse me, we're going to keep the bottom half of the ketone exactly the same. And we're going to have our double bonds. And then we attach to nitrogen. And coming off of nitrogen, we have an OH. And this guy is the oxime. Yep, that's it. We did a bunch of those reaction mechanisms, and at this point, they're all pretty much the same. So I'm giving you like the short versions. If anyone wants the longer versions, I can draw them out for you, but I think it's better for everyone's mental health if we just do the short versions. Like, I can draw it of the first step. So it'll be like that. And then eventually you can think of it as kicking off the original O and replacing it with the nitrogen. Yep, there's going to be 2 deprotonation steps. And if you think about it, that's a great segue, Leah. NaOH is a base. So how does the base affect the reaction? It makes the nucleophile more nucleophilic. Cool. And how does it do that? What? It does use its lone pairs to do something. It's probably a lot more straightforward than what you guys are thinking. It takes a hydrogen. So what is the buzzword for taking a hydrogen? Deprotonating. Cool. So again, a base is going to make the nucleophile more nucleophilic by deprotonating it. Yay. Okay. Questions, comments, concerns? How do we feel? So the thing, if you have an or asymmetrical ketone, like let's say you have that, right? You could get either this, or you could get this, but those are exactly the same answer. As long as you know you get one of those, you're fine. That's what you were asking, right? Yeah. Okay, cool. But it is worthwhile to note that these guys would be stereoisomers. Just know the buzzword. The reason they're stereoisomers is because the OH is pointing towards 2 different groups. So you technically would have a different, excuse me, E or Z configuration. It's a little bit weird because the nitrogen only has 1 substituent, but as long as you know they're stereoisomers, you're good to go. Okay. So now let's do the enamine reaction. And enamine sounds kind of similar to what? Yeah, for the imine. Cool. So I want you guys to think about the imine reaction while we do this one. And this is one that I actually, geez, I actually do have to draw some of the steps. So just bear with me. All right, so for the enamine reaction, we're going to use a nitrogen that has 2 different R groups and a hydrogen. So what would we call that? Secondary amine. Cool. And again, the reason this reaction is similar to the imine reaction is because imine uses what nucleophile? Primary amine. Cool. All right, and again, I'm going to use NaOH because it's that kind of day. So the first step would be what? Deprotonating. Cool. So it's gonna, bam, steal that hydrogen, and it would give these electrons back to the nitrogen. So in the first step, we did nothing to the ketone. That guy's just chilling. But we gave a negative charge to our nitrogen. So we made it a better nucleophile, and we also made H2O, which will be important later. So now we're going to attack, hello, bring those electrons up. And what happens to the hybridization of that carbon in this step? It changes, it goes from what to what? sp2 to sp3, cool. So I am gonna move this over a tad. I will zoom back out at the end, I promise. So we get bam, bam, we leave that bottom alone. Now we get O on this side, and we get N with 2 R groups and a lone pair. So do we have any charges present here? Someone said yes. What was that? Where? Do we? So usually we do end up getting a plus charge there because we have NH2, but in this case we got rid of one of the hydrogens, so it is neutral. But we do have a charge on the oxygen. Is it plus or minus? What do you think? Minus. Cool. Alrighty. So at this point, we're going to, what do you think? Something with the water, perfect. So the water is actually going to donate a hydrogen. So bam, bam. And in all the previous reactions, we had H2O as the leaving group. But in this case, if we used the base, which we did, you're going to get an OH instead of an H2O. And in this case, that will actually be a good enough leaving group. It's going to be a little smushed, but... All right, so if we make the OH a leaving group, how do we make it leave? Yes, so we're going to use the electrons to make a double bond. So bam, bam. So I'll draw down here. We get a double bond to nitrogen and 2 R's. Perfect. So are we done now? It has a positive charge. Woohoo. All right. So what is the easiest way to get rid of a positive charge? Okay, something about OH. Let's, not this one in particular, just in general. I've said a couple times, what's the easiest way to get rid of a plus charge usually? Deprotonate, cool. We cannot do that in this case because we don't have a hydrogen. So let's think back, right? What example have we done in this chapter so far where we had a similar situation to this and we had to get rid of the plus charge? There is. To do what? But how will we do that? So usually, yes, you're definitely right. We could use that negative charge to steal hydrogen, but in this case, there's no hydrogen here to steal. Attach what? We definitely could, except it would just go backwards because you can't directly attach it to the nitrogen. So let me scroll up and let's look at the lovely acetal-ketol reaction. So we had a similar situation here where we had a plus charge that we couldn't get rid of because there was no hydrogen. So what did we do in this case to alleviate? But how? We attack again, exactly. So we use another molecule of the nucleophile and we attack again. But what I want you to notice here is that oxygen only has one R group. So the problem with the enamine, the reason you can't just attack again, is because we consider this to be too bulky. So it cannot attack again. So we kind of have to get creative at this point. And what I know is that there's something called alpha hydrogens on that carbon, right? And I believe we talked about this a little bit, but alpha hydrogens are extra acidic. So we will actually be able to use our OH to steal one of the alpha hydrogens. And let's see what would happen if we did that. Bam. This is going to make a double bond here. And that would kick this double bond up here. So we end up with nitrogen gets a lone pair from that double bond. This carbon right here gets a double bond. And now there's only 2 hydrogens remaining here. So this is weird. This isn't like anything we've done in any of the other reactions this chapter. But essentially all we did is an elimination. And we gave those electrons back to nitrogen. And the key thing that I'm going to make a note of down here is we make a double bond specifically to the alpha carbon. And correct me if I'm wrong. We have talked about the alpha carbon, right, this semester? Somewhat, like a little bit? Okay. We're going to talk about it way more in the next chapter. But for now, all you need to know is that this was the carbonyl carbon. So the carbons coming directly off of it are called alpha. Any questions? Okay, so let me zoom out so you can see the whole thing. And I'm going to make a little note on the side right here. Yep. So the enamine is going to be the only one where you end up with a double bond that's not like of the carbonyl carbon to a heteroatom. So one thing I want you to note is when we're making the double bond, we're going to choose the more favorable side, right? So let's say we have a ketone like this, right? So we have this alpha position, we'll call it alpha 1, and we have alpha 2. Which one of those alpha carbons is going to make a better double bond? Ooh, okay. So some people said alpha 2, some people said alpha 1, so let's see. So if we do alpha 1, we end up with this and this. If we do alpha 2, we get this. So how do we know which one is better? The more substituted side, exactly. So this double bond right here has 2 substituents, whereas this double bond here has 3 substituents. So the more substituted side is always going to be the more favorable side. So we choose alpha 2. This tends to be tricky at first, but do we kind of sort of see why? Awesome. And the second thing for this reaction is, let's say we have something like this, right? Benzaldehyde, for example. How many alpha carbons does benzaldehyde have? Only 1. And does that alpha carbon have any hydrogens? No. So is this able to react with a secondary amine? No. So if he gives you something like this, where there's no alpha hydrogens, this is a trick question, and it is no reaction. And that happens, again, when there you go, when there are no alpha hydrogens present. Yes. Exactly. So what was that? Great question. So the question is basically, why can't we take this aldehyde hydrogen, right? So that hydrogen is directly attached to the double bond. So if you guys remember, that's called the phenylic position. The phenylic position is absolute trash. It's garbage. You never want to take that position because then you get a plus charge on a double bond, and we hate that. We do not want that. So it would be much, much, much more stable if we just leave it alone and don't react. Okay. All right, so again, let me just zoom out so you guys can take a look-see at this for a sec. And the next thing we're going to do is my favorite reaction of this whole semester. So I'm very excited. But in the meantime, we're going to get together and we're going to do some fun stuff on the board. So while I write stuff on the board, I want you guys to get in groups of 2, 4, 6. Let's say 4. 4, yes. So I'll give you like a minute while I'm writing. What? Okay. All right. And then I'm just going to use this for myself. So yes. What's up?
Quick question.
Yes. It is easier,
Yeah.
but we want the one that would make the most substituted size.
So that
So
beats that, I guess.
yes, so the extra energy it takes to get the harder
Yeah,
position
that's what I was thinking.
is B. Yep. Yes. If you look it up, he has a Facebook. I highly recommend you look at his Facebook. It's a good time all around. Lyndon. No, his real name. It's just Lyndon. Alrighty. Okay, so I am going to pause the recording. Okay, so let's go through the answers. And for some of these, I changed it around a little bit from what was on the handout. So I just made like a new page and I wrote them all down for you guys. So number one, it said that it is, or someone, I don't know who it was, said it's an acetal reaction, and that is correct. So how did you know it was an acetal reaction? What gave it away? I mean, yeah, but like what reagents do we have? Yes. Perfect. So we had an aldehyde plus an alcohol and acid. So what you guys wrote was that we go all the way to the acetal, which has two OR groups. So we're just going to copy the bottom part of the aldehyde. And then we replace the double bonded O with two OR groups. And this is in fact an acetal. Yay! Any questions on the first one? Cool. All right. So the second one, they said that it is an imine. Does everyone agree? Yes. And the reason it's an imine is because we have a primary amine. And all we have to do, like it's drawn on the board, is keep the bottom ketone part exactly the same. And we replaced O with a nitrogen. And the nitrogen had a methyl on it. So we add a methyl. And this is called an imine. Any questions? Cool. All right. So the next one, they didn't name it, but does anyone want to tell me what the name of this reaction would be? The enamine. Cool. And the reason we know it's an enamine is because we have a secondary, oopsie. We had a secondary amine. And what they showed us is that we're going to replace the, sorry, writing and talking at the same time. We replaced the double bonded O with a single bonded nitrogen, and we attached the R groups that were present. And then they drew the double bond to this side, and I absolutely agree with them because that's the more substituted double bond. Any questions about this answer? Was there a question? Did I imagine it? Okay. No, yeah, it's fine. I'm used to it. Didn't mean it like that, but it's already been said. All right, so number 4, you might not be able to see it down there, so it's fine. But they said that it is the Phenyl Hydrazone reaction. And we know that because we have the Phenyl Hydrazine. And the product they drew kept this aldehyde part exactly the same. And all they did was replace the double bonded O with a double bonded N. And then that N was attached to an NH and a phenyl. Ta-da! And I don't want to write that out again, so I'm just going to bam. Any questions? Okay. So number 5 was the weird one. It had the excess, and as I mentioned, this is still called the Hydrozone reaction. Although the product has a different name, which you don't have to worry about. And so the first step was keep the bottom part the same, replace with the nitrogen. And in the second part, we took the other nitrogen, and as these lovely people drew out, we add another mole of that ketone to it. And this is another one of those where it doesn't matter like which way the R groups of the ketone are pointing, as long as you know the general idea of what this looks like. So number 6, we said it was the Oxime reaction because we see a hydroxyl amine. And what the lovely assistants did was they kept this ketone part the same, and they replaced the double bonded O with a double bonded N, and there's an OH pointing here. On the board, they just drew it on the other side, but it doesn't really make a difference. And we call this the Auxime. Alrighty, and for number 7, we got a big, bold, red no reaction here. And it doesn't say, but what is the name of this reaction, if it were to happen? The enamine, yes. Because it has a secondary amine. And why did we say no reaction? Too bulky, too substituted, aka the 2 alpha carbons do not have any hydrogens present. So there's no alpha H. So it's no reaction. Perfect. And last but not least, before I give you guys the answer for this, what is pyridine? It is just a base. So all you need to know, pyridine equals a base. So it wouldn't change anything about this reaction. And that's why they said that it is an imine reaction. And all we end up doing is keeping the ketone part exactly the same, replacing that O with an N. And we have 3 carbons attached to it. So we go 1, 2, 3. Ta-da! So let me try and zoom out and put all of them at once, if I can. Hold on, I'm determined. Good enough. Alrighty, so that concludes what we're doing today. Unfortunately, we didn't get to my favorite reaction today, but we will start with that on Monday. Any questions, comments, or concerns before I let you go? Okay, cool. Please take some candy on your way out. I have too much.